Hello, class. My name is Garrett Levesque, and I'd like to do a presentation for you on oxide nanoparticles. I'd like to begin with structure. With polymorphic solids, it is possible to synthesize selectively one or other of the crystalline forms by controlling different parameters. With titania or titanium dioxide, which mainly exists as three polymorphs, namely anatase, brookite, and rutile, following increasing thermodynamic stability. When a solution of titanium tetrachloride, strongly acidified by a non-complexing acid such as perchloric, is heated around 100 degrees Celsius for some days, nanorods of rutile are progressively obtained, and in such conditions, the three polymorphs are initially simultaneously formed in variable proportions, but the dissolution crystallization process transforms the less thermodynamically stable phases, anatase and brookite, into rutile. I'd like to continue on structure now. The three polymorphs of titania can also be selectively obtained from oxidation of titanium-3 soluble species in acidic media or solid phases with pH of greater than 3. In these conditions, the control of the acidity of the medium allows one to control both crystalline structure and morphology of titania nanoparticles. I'd like to now continue with properties of oxide nanoparticles. They can be semiconductor, metallic, or insulating. And additionally, the mechanical, electrical, and chemical properties can be tuned based on the size and shape of the nanoparticles. And also particles of copper oxide, zinc oxide, tin oxide, dialuminum trioxide, magnesium oxide, zirconium dioxide, silver oxide, titanium dioxide, and cesium oxide, in addition to many others, are found. Lastly, the unique chemical and physical properties of oxide nanoparticles are attributed to the high density and limited size of corners and edges on their surface. I'd like to continue now with properties. As the size decreases in the nanoparticles, an increasing number of surface and interface atoms generate strain or stress and adjoining structural perturbations. Additionally, iron oxides, particularly magnetite, are of particular interest to material scientists as they are connected through a series of potential applications extending from magnetic storage devices, MSD, to magnetic resonance imaging, MRI, contrast agents, and the MRI contrast agents are used in hospital settings. Lastly, germania, or GeO2 nanoparticles, have many prospective applications for enhancing optical fibers and other optoelectronic fields. Now I'd like to get into the applications of oxide nanoparticles, and I'd like to start with gas sensors. And with some distinguishing advantages, such as larger range of operative parameters to be analyzed, such as in rapid fluctuations in light intensity, polarization, and wavelength modulation, in addition to others, selectivity improvement, and easy implementation, oxide nanoparticles allow better signal transport, in situ monitoring, and potential to be exploited by using surface plasmonic resonance, which improves the sensing performance. Owing to more surface active sites, large surface to volume ratios, high specific surface areas with very high surface reactivity, and nanometal oxides are applied towards gas sensing. And in gas sensors, there's a wide range of applications for oxide nanoparticles, and they're used, in addition to many others, in carbon dioxide, carbon monoxide, oxygen, ozone, nitrogen dioxide, nitric oxide, methane, hydrogen gas, hydrogen sulfide, and ammonia gas sensors. My next application I'd like to discuss is in batteries. And to enhance the performance of lithium-ion batteries, researchers gave excessive prominence to develop novel electrode materials with nanometal oxides that have been used traditionally for several decades by researchers. And recently, researchers focus on the synthesis of multiple, 4 or 5, transitional cationic oxides in equiatomic amounts stabilized in single rock salt structure, or the so-called high entropy oxides, HEOs. Next, I'd like to talk about the application in solar cells. And in cuprous oxide, or Cu2O solar cells, it's a p-type semiconductor that's attractive as a photovoltaic material because of its low cost, high absorption coefficient, good mobility, great availability, and non-toxicity. And here we see the back wall cell and the front wall cell with the semi-transparent metal film electrode, the Cooper's oxide, and the copper. And then additionally, we see in the front wall cell the semi-transparent metal film electrode. I'd like to talk a bit more about solar cells. In the binary heterojunction of two semiconducting materials, where one of them displays a higher affinity to electrons, whereas the other to holes, local electric field increasing excitation and current is created. As doping of N-type Cooper's oxide is persistently hindered, a relevant bilayer zinc oxide, either planar or nanostructure, was used as oxide window for Cooper's oxide absorbers. Additionally, the all-transparent solar cell can be attained by the heterojunction metal oxide material with a wide energy band gap for power generation. Now I'd like to talk about thin film solar cells. And in a thin film or TF solar cell, also known as a second generation solar cell, is made by depositing photovoltaic material as several thin layers or monolayer on different substrates such as glass, plastic, or metal. Compared to conventional semiconductors, ferroelectric solar cells demonstrate several orders of magnitude higher photovoltaic voltage than the corresponding band gap of the material and ability to regulate the photovoltaic characteristics by electric field. Barium titanium oxide thin films have been extensively studied ferroelectric material over the years because of the wide range of applications. Next, I'd like to talk about dye-sensitive solar cells, otherwise known as DSSC or DSC, or third-generation solar cells. And they contain a thick film of semiconductor nanoparticles, a monolayer of organic dye molecules adsorbed to the nanostructured layer, liquid electrolyte, and counterelectrode. And in this diagram, you can see the light passing through the glass and the TCO. You've got the dye at the bottom, you've got the nano-oxide in blue, and then you've got the electrons passing through. The next application I'd like to discuss is antennas. Antenna converts electromagnetic radiation in space into electrical current. The main idea of an antenna is to conduct electricity, as radio waves are one form of electricity. So it is certain that an antenna must have conductivity and should not get oxidized. And the best way to overcome this oxidation is to call upon metal oxides that are stable enough to be used as antennas. And they seem to be an alternate source as antenna materials. I'd now like to discuss one application of antennas, which is optically transparent antennas. And they're presently available in four kinds. The first kind is a metal oxide film, otherwise known as ITO film. Within the antenna design, a compromise must be made between the light transmittance and the surface impedance. The next kind is multi-layer silver-coated polyester thin film, such as AGHT series. And compared with the ITO film, the AGHT film has better conductivity, but worse transmittance. The third kind is an ultra-thin metal film made of copper, silver, gold, or other metal conductors. And such antennas have high radiation efficiency, yet pretty low light transmittance. And the final kind is metal mesh antenna, which demonstrates the highest radiation efficiency and light transmittance higher than that of the ultra-thin metal film. However, it has high requirements for processing technology, so that's the downside on that one. The last application I'd like to discuss is optoelectronic and electronics applications. And the specific type I'd like to talk about is the P-type transparent conducting oxide. And amid numerous oxide materials available, the utmost significant oxide-based material which creates maximum attention for material scientists is semiconducting transparent films, better known as transparent conducting oxides, or TCOs. Because of their unique properties, they are intended to be extensively utilized for essential aspects of long-standing applications in optoelectric industries as solar cells production, but also for flat panel displays, LEDs, touchscreens, and low emissivity windows, etc. Now I'd like to show a video on the synthesis of iron oxide nanoparticles. And I apologize, it's a little bit hard to hear at the beginning, but then it becomes easier.
Uh, Spirit, hoping for the spirits to run on us and become a part of our glory. Prepare yourselves to go into a new dimension. Are you ready?
There's that video. I have one more video to show you. And it is zinc oxide nanoparticles. Here we go.
I'm Marzi Hosseini and this is Nanotechnology channel. In this video, I will describe green synthesis of zinc oxide nanoparticles using extract of aerial part of Devereux tortuosa as a reducing and capping agent. Devereux tortuosa is a wild perennial bushy plant growing naturally in sandy and stony plains. Zinc oxide nanoparticles have wide bandgap, large binding energy, and high piezoelectric property. Zinc oxide nanoparticles are believed to be bioself, non-toxic, and biocompatible. Zinc oxide nanoparticles have applications in optoelectronics, piezoelectric and magnetic sensors, biological labeling, biodiagnosis, ceramic and rubber processing, biology and medical industry, environmental protection, and so on. The surface of zinc oxide is rich in hydroxyl groups, which permit zinc oxide to slowly dissolve in both acidic and strong basic conditions. Based on this property, zinc oxide nanoparticles have gained interest in biomedical applications. In the green synthesis of zinc oxide nanoparticles using extract of aerial part of Devereux tortuosa, the first step was plant extraction. At first, plants were washed with distilled water to remove any debris, then dried at room temperature. Aerial parts were finely ground into a fine powder. Then the aqueous extract was prepared. 50 grams of the plant powder was soaked in 1 liter of distilled water. It was kept in a shaker at 20 degrees centigrade for 24 hours for continuous agitation at 100 RPM for mixing. Then the extract was filtered and stored at -4 degrees centigrade for further investigations. The next step was synthesis of zinc oxide nanoparticles. At first, 25 milliliters of the crude plant extract was heated on a magnetic stirrer at 60 to 80 degrees centigrade. When the temperature of the extract reached 60 degrees centigrade, 2.5 grams of zinc nitrate hexahydrate was added and left for about 1 hour until a white precipitate appeared. This mixture was left 12 hours in an oven at 60 degrees centigrade until a creamy paste was formed. This paste was collected and washed several times with a solution of distilled water and ethanol. Then the collected paste was heated in a furnace at 400 degrees centigrade for 2 hours. The obtained white powder was used for characterization. X-ray diffraction pattern of synthesized zinc oxide nanoparticles is displayed in this figure. The maximum intensity peak at 36.24 degrees was obtained with 101 orientation. The sharpness in the peak endorses that synthesized material is crystalline. The average crystallite size of zinc oxide that measured using Scherer's formula was 15.41 nanometer. In this slide, you can see the TEM analysis of the synthesized zinc oxide nanoparticles. TEM analysis can be used to understand the crystalline characteristics and size of nanoparticles. According to this analysis, the size of particles was between 9 to 31 nanometer. At the end, please make sure to click the subscribe button and to hit the notification bell so you know exactly when we release new contents. Also, right now, comment below and tell us what topic you want us to cover, as we always look at the comments to decide what to create next. Bye.
I hope you enjoyed that video on the green synthesis of zinc oxide nanoparticles. Lastly, I'd like to discuss the references. And this Springer.com article discussed the applications and properties, which I used extensively in this presentation. In addition, the Science Direct article mostly covered the structure of the oxide nanoparticles. And then the two YouTube videos discussed synthesis of both zinc oxide nanoparticles and iron oxide nanoparticles. And with that, I'd like to thank you for watching my presentation.